start. I think it's going to be on regression.
So I hope by now I don't have to introduce myself again. By the way, some people still call me Dr. Sharma. I'm good with the tool. I had a patient who insisted to call me Butthead. But his dad said, but he means it in the best way possible. In any case, today, this is probably the most advanced topic, and it kind of wraps up what we've talked about before. We're really talking about statistical modeling today. I have tried to put, there's more information in the primer than in this talk, so I would urge you to actually refer to the primer. Now, up till now, we focus mostly on some basic statistical theory, descriptive statistics, methods of comparisons. Has everybody had a chance to look at the t-tests and the test comparisons of proportions that we didn't cover, or should I plan to cover it at some point?
It'd be bad to cover it.
Okay. Okay, well, I know you have some flex time today. I only need about 10 minutes. I may eat into your flex time.
That's okay.
Okay.
So yeah, at around 10, I've asked whether Dr. Chu can come at 9:30 instead of 9. And I did not arrange for Jonathan and me to be sitting next to each other in advance. But whether or not we just start by Dr. Chu may start at 9:30.
Yeah, and if he can, I'll just come back after him and we'll finish up. Okay, that's fine. It's either way, we'll do that. So today we're going to move on to what is called the generalized linear model. And most of you should be familiar with the standard linear regression model because you've covered it in introductory statistics at some point. It's a pretty basic tool. And what I really hope to do today is to show you how you can leverage what you already know about this ordinary linear regression model, which is called LM, or linear model, or ordinary least squares, or OLS model, and how you can leverage what you already know to analyze any type of data that you're likely to encounter. And for that purpose, we're going to talk about the generalized linear model. And it really will turn out to be a very versatile tool in your statistical toolkit because it unifies a huge swath of modern statistics in a common framework and a common language. And if you're familiar with the generalized linear model, you really should be able to make sense of much of the literature you're exposed to. We've already said many times that a meaningful research question depends on having clear exposure variables, clear outcome variables, and a question that relates the two. The most important of these is the outcome, or the response variable. And as I've said to you several times, the reason it's important, in part, is because once you've decided on the nature and the type of your outcome variable, the statistical analysis follows automatically. Now, this may surprise you. 1989 was within my working lifetime. In fact, Celia and I were chief residents together at the time, and Nelder and McCullough came out with this textbook called the Generalized Linear Model. So it's a relatively new concept, in which they said everything we know about regression can be extended to virtually all statistical analyses. So if we have a continuous numeric variable, or response variable, or Y variable, like height or weight or birth weight, then we can assume that that Y is normally distributed, and we can do a multivariable linear regression that you guys should be familiar with. But by tweaking the model a little bit, we can make it more flexible. So if our outcome is a yes, no, heads, tails, binary categorical response variable, we can assume a binomial distribution, which is the coin toss distribution that we've talked about, and we can do what's called a logistic regression, which you'll learn about. If we have more than two categories that are nominal, we can assume a multinomial distribution and do a multinomial regression. But they're all regressions, and they all have the same language and the same structure and the same interpretation. Similarly, if we have ordered categories, we can do proportional odds or adjacent category logistic regression. If we have count data, we can do a Poisson or a negative binomial regression. And perhaps the most confusing, if we have survival time data, or time to event. So it doesn't have to be death, though it often is, but it can be time to relapse, time to complications, time to stopping breastfeeding, which is one of the examples we're doing. And one of the complications with time to event data is that they are usually what we call right-censored, which means that some patients had the temerity to still be alive at the end of the study. They were lost to follow-up while they were still alive. So you don't know if they're going to live for 12 more months or die the next day. And if you just throw those patients out, you're going to bias your results because these are the survivors and you're excluding them. And so time to event analysis wants to make use of all the data we have up until the time we lose them to the study. And that's actually a very complicated methodology that we'll talk about in a little bit more detail later on. But in 1972, Cox published a paper saying there's a regression model that can accommodate right-censored time to event, and it's called the Cox Proportional Hazards Regression Model. That paper from 1972 is still the most frequently cited statistical paper in the medical literature. So whether or not you want to, you are going to have to be familiar with the Cox regression model. And in fact, it probably came up in one of your journal clubs. Oh, I know the obesity, the long-term follow-up of the Israeli teenagers. They did a survival time analysis using a Cox model. So we're going to talk about the Cox model as an example of the generalized linear model. Because you are going to meet it in your readings. So firstly, I want to say something that's basic and fundamental to the topic. We've looked at these 189 newborns from Springfield, Massachusetts, and we've done a t-test to look at the relationship between the mean birth weight, comparing it in our race categories. And you'll recall when we had two race categories, non-whites were 320 grams lighter, the t-statistic was 3.1, and the p-value was 0.002. We've seen that already, and we'll do it again in the lab. But it might not be so intuitively obvious to you that we could have framed that same question as a regression, where the left-hand side is a continuous numeric birth weight, and the right-hand side is what we call the linear predictor. So in this linear predictor, beta naught is the intercept. It's the value we expect for y when race equals 0. So white equals 0 is our reference category, so beta naught is basically the weight of the white babies. And beta 1 is now measuring, as it always does, the impact of a unit change in the corresponding predictor. So if a race goes from 0 to 1, beta 1 gets added to the white birth weight. So that's what the beta 1 regression coefficient means. And so if we frame this question as a regression, you'll see white babies are 3,102 grams, the difference is 320 grams, the t-statistic is 3.1, and the p-value is 0.002. So the point I'm trying to make here is not that these are similar tests, these are identical tests. So we could easily have framed our t-test as a logistic regression and gotten the same results. Similarly, you will remember that we looked at the 2x2 contingency table where we cross-tabulated low birth weight and race, and we calculated a chi-squared test for independence between the row and column variables. And we calculated a chi-squared statistic of 4.1 with a p-value of 0.04, and we concluded that there was an association between low birth weight and race, and we even calculated an odds ratio of 2.005. Well, that too could have been framed as a regression. So in this case, we have a binary outcome, and you may remember a moment ago I said for binary outcome, we do a logistic regression. So what does that mean? A logistic regression is shown here. The right-hand side is the same linear predictor we just saw. So beta 1 measures the impact of going from white to non-white race on the left-hand side. The difference is that the left-hand side is now the log of the odds. That's the definition of a logistic regression. So this is called the log odds or the logit of p, where p is the probability of low birth weight. And so we're saying I want to find the regression relationship between this logit transform, and the only reason I'm using that word is because you'll often see this referred to as the logit model. I want to fit this model to the data. Now, in this case, beta 1 is measuring the impact of race on the log odds. Well, I don't really care what its impact is on the log odds. I want to know what its impact is on the odds ratio, which I calculate by taking beta 1 and taking its anti-log or exponentiating it, e to the beta 1. So in R, I say, please fit this regression model, and instead of using the LM function that we used a moment ago, I'm going to use the generalized linear model function. I don't have to calculate the odds, I just have to tell it what my low birth weight indicator is. It'll do all the calculations for me, and I say, please regress it against race, and the intercept gets included by default, though you can remove it. If you wish, though that's rarely a good idea. And in this case, I say it's a logistic regression because I'm assuming a binomial distribution. So that's how I tell the GLM function that this is a logistic regression. And so I get my estimate for beta 1. It says that when I go from 0 to 1, a unit change in x, the log odds goes up by 0.695, which corresponds to an odds ratio of 2.005. Exactly the same odds ratio, exactly the same p-value within rounding error. So again, these aren't similar tests, they're the same test. Now, you might fairly ask me, well, if they're the same test, why bother? And I might be honest with you and tell you, well, in 1989, this was the kind of geeky thing I would drop into dinner time conversation to convince Celia to go on another date with me. But the truth is, there are advantages to this regression approach, and it particularly has to do with non-randomized or observational data. So I know you spent 2 hours discussing confounders, so I'm not going to review them in detail, but you do appreciate that in non-randomized studies, the groups may not be comparable. They may differ in age and sex and disease severity, or even in a randomized study. Sometimes the randomization procedure fails. And then you get what are called selection biases, which are just differences between the groups. Now, confounding occurs when those differences influence the outcome. And so, I'm not going to summarize, I think it was Megan Zada gave you a long talk on confounders. I can't summarize that whole talk, but I am often asked, how do I know when to worry about confounding? So the best operational definition I can give you is potential confounders are third variables that are correlated with both your exposure and your outcome. And any variable that is in that situation is a potential confounder, and you have to worry about it. So just to give you a comprehensible example, we know in the United States that non-whites smoke more than whites. In fact, the odds ratio is 3.8. The chi-squared statistic is highly significant. And that could be a confounder. That could be explaining the racial difference in birth weight that has nothing to do with race. So using chi-squared statistics and 2x2 tables, it's hard to tease that out. But in a regression framework, it's actually very easy to address. This is our logistic regression model. It's exactly the same as before, except I've now added smoking, which is a yes-no variable, 0 for non-smoking mothers, 1 for smoking mothers. I ask R to do this more elaborate logistic regression model, and watch what happens. When I adjust for smoking, the impact of non-white race is actually greater. This is not a confounder. It's it's actually masking. It's technically a confounder, but it's not explaining the effect. It's masking the effect because our odds ratio goes up from 2 to 3, and our p-value gets stronger. It goes from 0.03 or 0.04 to 0.002. Similarly, when I control for race, the impact of smoking is quite dramatic. It increases the odds of low birth weight by a factor of 3, and the p-value is highly significant at 0.002. So this is a very simple example, and I hope it shows you how the regression model can accommodate multiple predictors simultaneously, how it can allow you to assess their effects independently, and how, in this particular case, it can help you answer the question about the role of confounders, because we've identified a potential confounder and now we've asked ourselves, what is it doing to the effect? And so these odds ratios are what we call adjusted odds ratios after adjustment. And these regression coefficients are what we call partial regression coefficients. We'll come back to what that means in a bit. But basically we're saying, what is the effect of race? Smoking held constant. What is the effect of smoking? Race held constant. And we'll see why that is in a little bit. So before we get into the meat of the day, I wanted to give you some common examples. These are data we looked at earlier, where we looked at the incidence of septo-optic dysplasia in Manitoba, which is a count variable, and our single exposure was year, which is a continuous variable. So this was the graph with the lowest smooth, showing that something appears to happen in about the year 2000, and we started to get a non-linear, almost exponential increase in annual incidence. So for count data, as I mentioned, we often do what's called the Poisson regression. So the Poisson regression has the same linear predictor. Beta 1 measures the impact of a 1-year change in time on, in this case, the log of the counts. Not the logit, not the unconverted, untransformed counts, but on the log of the counts. Someone mentioned yesterday the incidence rate ratio. So let me define that. I'm not really interested in the impact of year on log counts. I want to know what the impact of year is on counts. So if I exponentiate both sides, I get counts, and then I get e to the beta on this side, so the anti-log of beta, and that's the incidence rate ratio. It tells me what's the impact of this predictor on the counts. The key thing to remember is the incidence rate ratio is multiplicative. So if in this year I have 10 cases and my IRR is 2, then next year I expect 20 cases. So it's a multiplicative factor, and the reason for that, you'll remember from high school algebra, is that adding logarithms is the same as multiplying on the non-log side. Okay, so that's not complicated. In this case, we use the GLM function. We say we want to regress counts against year with an intercept, and it's going to be a Poisson regression. So we tell it family equals Poisson, and we get an incidence rate ratio. And firstly, we get the beta. So basically, this is telling us the log counts goes up by 0.11 for each year increase, and we get the incidence rate ratio is 1.11. And you remember this applied over 20 years. It's multiplicative, so each year it's 1.11 times 1.11. And so over 20 years, we expect an 800% increase. And that's exactly what we're seeing. We went from about 1 to about 7 or 8. This dashed line here is the predicted line from the best fit Poisson line. And you can see it actually follows the lowest curve quite nicely, just to make the point that generalized linear models are not limited to linear relationships. In fact, that's why there's all those logarithms and logits and other transforms in there, because in this case, that's a pretty darn good fit. I'm going to show you one more example before, yeah, sure.
The Poisson was because there were low numbers of counts.
No, more because they were counts, so they can only take discrete integer values. So it doesn't have to be low number of counts, but often when it's a high number of counts, there are so many possibilities that you can treat it as continuous, because it can be 794, 795, 1012. You can treat it as continuous. But even then, you may want to, you should use the Poisson model, because the linear model may give you a prediction that's a negative number. And the Poisson model won't, because counts can only take 0, 1 values. And so if it's count data, the Poisson distribution is a better model, a better probability model than the Gaussian distribution, which can take on any value. Right. There's also another negative binomial model, very similar to Poisson, when Poisson doesn't, that we use. And we're going to talk a little bit. I mentioned a moment ago survival time data, because it's right censored. So here's a very small study. Actually, this was one of the studies that Cox used in his 1972 paper. 23 patients with AML. One group got standard therapy. That was treatment equals 0, so they got treated and then stopped. The other group got extended therapy, so they got additional cycles of chemotherapy. And if this were a randomized study, and the groups were completely equal, all we're really interested in is comparing survival in the two groups, assuming everything else has been balanced by the randomization. And so you can see here, this is a Kaplan-Meier curve. And the way the Kaplan-Meier curve deals with the censoring is fairly straightforward. If a patient is alive here, they're counted in the denominator when we calculate the survival probability. If they are lost to follow-up, and you can see the little vertical bar tells you when the patient was censored. So that patient, the study ended and that patient was still alive at that point. And so that patient would count for this interval, but not for this interval. And so that's how we calculate survival probabilities for a Kaplan-Meier curve. And in fact, this is news to me, but we had a JAMA paper recently, and I discovered to my horror that JAMA now insists that whenever you submit Kaplan-Meier curves, you use these vertical bars to indicate censoring, and at the bottom you include a risk table that shows how many patients were actually at risk at each time point. And they will send it back to you if you don't do that. So now, in this case, we can calculate the median survival from our Kaplan-Meier curves, and we can see that it appears that extended therapy appears to increase the survival from 23 weeks to 31 weeks. But the p-value was not quite statistically significant. And in fact, we would call this a trend. It's between 0.05 and 0.1. We can't call it statistically significant, but there may be something there, particularly because our n was so small. So we could say, well, there's a trend and this deserves further study. Now, I think I mentioned in the primer when we talked about chi-squared tests. Remember, chi-squared tests are what we use when we're comparing observed minus expected counts? Well, that's what we're doing here. We're comparing observed minus expected death counts under the null hypothesis that they're equal in both groups. And so it shouldn't surprise you that the test statistic is a chi-squared statistic, and instead of being 4.1, which it was in our previous example, it's now 3.4, and that doesn't quite achieve statistical significance. But there's a unity here that it's a chi-squared test. So that's how you would do a conventional two-group comparison for survival. But let's say this wasn't a randomized study, or the groups were not equal, or we had additional predictors we had to adjust for. Well, that's where Cox said, oh, we can do this as a regression model. And the Cox regression model is just this. The right-hand predictor is the linear relationships that we're interested in studying, the most important one in this case being treatment. which is a 0, 1, or yes/no variable. And the left-hand side, though, is not the survival time, it's the hazard function. And it's the log of the hazard function. And the hazard function is just the probability of dying on day 7, given that you were alive on day 6. And that's called a conditional probability, that given that you were alive on day 6 is the conditional part. And that's how the Cox model deals with the censoring. Again, the denominator just keeps changing. Beta 1 is going to measure the impact of treatment on the hazard, on the log hazard, but I really want to know what its impact is on the hazard ratio, and so I have to take the anti-log. And so when I run the Cox proportional hazards regression model, saying regress survival time against treatment, I get the beta, which is minus 0.92, and I get the hazard ratio, which is the risk of dying in the treatment group divided by the risk of dying in the control group. And you can see here that the hazard ratio, which is the anti-log of the beta, is 0.4. So treatment appears to decrease the risk of dying by 60%. That's the hazard ratio, and you can see the p-value is again marginal at 0.07. So you see we get the same answer, except we get it from a regression model. And I will just mention, for completeness sake, that we have assumed that the risk of dying is the same at all time points. That's the proportional hazards assumption. That's why it's called the proportional hazards model. 5 years ago, you could publish a paper and you would probably get away with it if you said, I assume that that proportional hazards applies. In this day and age, reviewers are getting more clever. They see, oh, the method is called proportional hazards. That's a pretty important assumption, and almost every paper, people ignore me when I say you have to do the diagnostics that show that proportional hazards apply, and then the paper comes back and it says, did you check for proportional hazard? It's very easy to check, but just to make it clear that these are assumptions that they do have to be checked. So I have given you some examples. I wanted to spend the first 20 minutes just walking through some examples illustrating how generalized linear models work. You will have noticed perhaps that the Cox proportional hazard function doesn't use the GLM function. It has its own from the survival library. That's just for historical reasons. It is a generalized linear model. So let's talk about the generalized linear model. As I mentioned earlier, it really is, and it should be clear from these examples, it's really just the familiar regression model generalized to unfamiliar data types. It's a multivariable model, so it can handle multiple predictors simultaneously and allow you to assess their effects independently. By framing everything as a regression question, it gives you a consistent and a unifying framework, which I do believe quite strongly makes it easier to understand. And as we've seen, it's a good way to control for confounding. It's not the only way to control for confounding. You can match patients for age and sex and disease severity and then compare the matched pairs. You can do stratified analyses where you analyze homogeneous subgroups like adolescent males with severe AML. These are all legitimate ways to deal with confounding. The problem with matching and stratification, which make them less popular, is they really don't work very well with more than 2 or 3 matching factors, whereas regression modeling can handle dozens or hundreds of covariates or predictors, additional predictors in the model, as long as you have enough data. Now, Suzanne asked a question very early on that I said I would get back to, and it was a very important question, and so I am going to answer it today. Please do not be fooled into believing that it can prove causality in any analysis based on cross-sectional data. Even though these fancy regression models are nice, the data is at one point in time, and all I can talk about are associations or correlations. This is the relationship, the temporal evolution of organic food consumption and autism. And the correlation is 0.99. That does not prove that organic food causes autism. Only an experimental design, an appropriate experimental design, can prove causality, and typically a prospective randomized control trial. That's what they're really good for. And when we're dealing with these statistical models, to interpret them properly, you have to remember that these are just correlations, and you have to throw in a good dose of clinical understanding of the biology, which is where your expertise comes in. So I hope that answered your questions. I didn't want to be on the wrong side of history. I hope I've made it clear that all these regression models share the regression framework in common, and therefore it really is an advantage if we understand the conventional, familiar linear model. So I'm going to talk about it in some detail, and then I'm going to talk about how the generalized linear model differs from it. We went back and forth, Celia and I did, the best way to present the generalized linear model, and rather than presenting the entire generalized linear model theory, I think we make sure we understand the linear model, and then we talk about differences. And if that doesn't work, please feel free to tell me and we'll revise it. But that was our goal. So I try not to show you equations except where they're helpful, but here's the standard regression equation for the ordinary least square linear model. And we have n observations, which we're going to index by I. For each observation, we have a y value, which is the dependent variable. We also have a bunch of x's, which are the independent variables or the predictors. And each x has a beta attached to it, which we'll talk about in a minute. But for each observation, there's also an error term, usually called epsilon. And for the standard linear model, epsilon is assumed to be normally distributed with a mean of 0 and a constant variance of sigma squared. And we call that IID assumption, which is just independent, identically distributed, in this case, with a normal distribution. And then the betas. So in each case, the beta tells us something specific. Beta naught is the intercept. It tells us what value of y we expect when all the x's are 0. Okay? Now, please bear in mind that sometimes the intercept is biologically nonsensical. Like, for instance, we say, what's the mother's IQ, or what's the child's IQ when the mother's IQ is such and such? Well, the mother isn't going to have an IQ of 0. That intercept doesn't make sense. And usually that doesn't matter because we don't interpret the intercept that way. But if you want to interpret the intercept meaningfully, just center your data, subtract the mean, and then the intercept becomes the expected value of y for the average patient in the sample. So it's very easy to make your intercept meaningful if that's like giving you a headache. And sometimes it does get confusing, and I like to center. There's a center command that'll do it for you. It'll take care of all of them at the same time. The other regression coefficients or model parameters are the partial regression coefficients, and understanding their meaning is really important. In each case, it should be obvious that the betas measure the impact of a unit change, of 1 unit change, in the corresponding x. The caveat that's important is when all the other x's are held constant. And so again, sometimes that's not biologically plausible. It's hard to imagine weight being held constant without height changing, but for instance. But nevertheless, that's what it means. It is the independent effect, everything else being held constant. Now, by this point in our talks, it should be clear that we rarely know the population parameters, the betas. The best we can do is estimate them from the sample. And so just to make it clear we're dealing with estimates, we put a circumflex over them. And because we're really clever in statistics, we call these hats. So this is y hat, and these are beta hats. And our job is to estimate the beta hats using our data. And in the linear model, we do that by minimizing what's called the error sum of squares. So each observation has a residual, which is just the difference between the actual value of y and the predicted value of y. So y minus y hat. We square those residuals, we add them up, we get our error sum of squares. The ordinary least square procedure, which is also known as the LSE, or the least square estimation procedure, chooses the beta hats that make this as small as possible. Now that's a problem in first year calculus. I actually remember I got that at Dalhousie as a homework exercise in first year calculus. So I'm going to assume that you guys have too, and you could at least see, oh yeah, that's answerable. Take the derivative with respect to beta, we set it equal to 0, and we solve for beta. And so the beauty of this procedure is that you can actually get a formula that says beta hat equals. And you'll see that isn't always the case with the generalized linear model. So just to graphically show you that, this is the relationship between height and weight in Celia's diabetes clinic. And the intercept was 94.1. And for each year of age, on average, the kids added about 5 centimeters to their height. This is the best fit line using these values of the beta hats. and that minimize the sum of squared residuals. And these are the actual observed points and the residuals, just graphically to show you. The residual is just the difference between the observed and the
What does
expected.
the line mean? Not the main lines, but all the little lines. That's just a decorative way of drawing them.
Sorry, these vertical lines?
Yeah.
Yeah, so that's just the residual.
Okay.
So I'm just trying to make it clear what
Make
the
a visual
residual
of the
is.
residual.
Yeah.
It's
yeah.
like the R, right?
Yeah, that's right. So we're gonna square them, add them up, and the values of beta hat that make the total sum as small as possible are our estimates of beta hat. We have made some assumptions here. We've assumed, in this case, that the dependent variable is continuous, that it has Gaussian errors. We've assumed those errors are independent and identically distributed with a normal distribution that has a mean of 0 and a constant variance. We've assumed that the relationship between the dependent and the individual independent variables is at least approximately linear. And those are the standard big three assumptions in linear modeling. I add a fourth one to that, and it's really an absence of an assumption. I just want you to notice that I have made no assumptions about the x's. They can be anything. I just have to know what they are. But they can be nominal, ordinal, continuous. It doesn't matter. I have made no assumptions about my predictors. Now, it's important to realize that all statistical inferences, which means p-values and confidence intervals, depend on these assumptions, particularly normality and independence, and these assumptions have to be tested for. And there are, in fact, ways of extracting the residuals from any fitted model, and there are a whole bunch of ways of plotting those residuals to test these various assumptions. I'm not going to cover that in the talk, but in the primer for the various regression models we cover, I go through residual diagnostics. And when you come to your own study, budget enough time to do the diagnostics. There are some misconceptions I want to address. People who are new to it say, oh no, but I'm dealing with nonlinear data. Yes, I understand the real world is nonlinear, but many nonlinear relationships can be approximated as linear. So clearly, height versus age is nonlinear at plateaus, but it's linear over much of its range, and even over its entire range, it is approximately linear. If you really need to deal with nonlinearities, well, the linear model can do that. You've already seen with the Poisson model how transforming to a mathematical transformation on the left-hand side, taking the log of the counts, linearized the relationship, gave me, even though it was a nonlinear relationship. If you have a curvilinear relationship, you can add higher order terms. So if we're looking at the relationship between height and age, I can add age squared or age cubed. And in fact, the rule of thumb is if the slope changes once, add a quadratic term. If it changes twice, add a quadratic and a cubic term. If it changes 10 times, do all the same thing up to x to 9. And so it is incredibly accommodating. You can model complex nonlinear relationships using the so-called linear model. It requires some judgment and familiarity, but there's even an algorithm where you can ask the computer to say, okay, I have x, find me the power lambda that will transform x so that the relationship will then be linear. And you can just say box Tidwell, give it the model you want, and it'll give you the power for you. If we have time, I'll show you how to use that. But this is not an obstacle. So I just want to take-home message, linear regression can flexibly model nonlinear relationships. The other sort of anxiety that I see often is people say, well, you've assumed this Gaussian relationship, or these Gaussian errors, and I'm not sure our errors are really Gaussian. Well, the truth is, every assumption about the error distribution can be relaxed. So if the variance is in your residual diagnostic plots, if the variances look to be non-constant, there's a procedure called weighted least squares that can deal with that. The non-Gaussian distributions we've seen with the generalized linear model, we can model a large variety of non-Gaussian distributions, Poisson, binomial, multinomial, what have you, Cox. Probably, I want you to be familiar with this. We're not going to cover how to do it in class, but it is a fundamental assumption that all our measurements are independent. So we're measuring blood pressure in a sample that patient A's blood pressure doesn't depend on patient B's. And that's not always true. So that's what we call the data are uncorrelated or independent, but sometimes they're correlated and dependent because the patients come from the same family, or because it's the same patient measured in repeated measures over time. And even though that sounds like a deal breaker, the truth is there are procedures called generalized least squares or mixed effects models. These are regression with random cluster effects. And one of your journal club papers, I recall when we summarized it, included a mixed effect. Oh, it was the one on melatonin. I think. They included a mixed effects regression model to deal with the fact that they were looking at the same patient with repeated measures. So just to be familiar that if we violate these assumptions doesn't mean we can't analyze the data, it just means we have to make our analysis more sophisticated. And so mixed effects regression model or random effects regression model are very common in the literature. At one time, 50% of my consults were having to do with that, and less so now that people are becoming more familiar with them. But you should at least be able to recognize when they say in the methods that, oh, they used a mixed effect model to account for clustering, why they did that. Okay. So at this point, I would have come in and said, or I initially said, well, we're going to talk about the GLM, and Celia said, no, you can't do that. And she's right. So what I'm going to talk, instead about the GLM, I'm going to talk, instead of going through its theory, I'm going to tell you how it differs from what we just talked about. So my assumption is that we all are going to be familiar with the linear model, and then we're going to have a little bit of familiarity with how the generalized linear model differs. So the linear model, you'll recall, assumes Gaussian errors. I can make, there's dozens of distributions that I can assume for the generalized linear model, appropriate for different types of data. You'll remember that in the linear model, we minimize the sum of squared residuals, or the least, that's called least square estimation. That's not how we fit a generalized linear model. A generalized linear model has a probability density function like we saw for the normal distribution. And it's called the likelihood function. And the maximum likelihood estimation procedure says, tell me which values of beta make the data that are in my hand the most likely data that I would see. Those are called maximum likelihood estimates. Now, as it turns out, for the Gaussian model, and this is only true for the Gaussian model, the least square estimates and the maximum likelihood estimates are identical. So, but that's not true for any other model. So for the other generalized linear models, we are not doing residual minimization. We are maximizing the likelihood of seeing the data that we're actually seeing. And unlike the least square estimation procedure, we don't have a nice formula that says beta hat equals this. The computer does an iterative trial and error search, and sometimes that search fails, and you'll get an error message that says fitting procedure failed to converge. And you're going to have to do some searching and try to figure out what you can do to make it converge. And so that is a little bit of a difference. But the benefits of that difference are that we can apply it to any probability distribution virtually. And there are some other nice advantages. For example, if our n is sufficiently large enough, our maximum likelihood estimates, or our betas, our beta hats, have some nice statistical properties. Firstly, they're normally distributed, and they're unbiased. Also, they're what we call minimum variance estimates. So, in fact, of all the linear models that we could fit, these ones have the smallest standard errors. And that can be theoretically shown to be the case. And so these are what I mean. Just knowing that the maximum likelihood procedure returns estimates that are normally distributed allows me to calculate p-values and confidence intervals, basically using the properties of the standard normal distribution. The nice thing about the procedure, even though it's an iterative trial and error procedure, it returns estimates of both the beta hats and the standard errors, so it makes it very easy to do those calculations. This is the linear model that we talked about. The right-hand side is the linear predictor. This is the generalized linear model. The right-hand side is, again, the linear predictor. The left-hand side is different, because we have to do a mathematical transformation of the left-hand side to linearize what is usually a nonlinear relationship. The function g that does this transformation is called the canonical link, or link function. If you want to consider the linear model as a type of generalized linear model, which it is, the link function is just 1 times y, so it's called the identity link. But each linear model has a different link function. So the logistic regression model had the logit transform. That's the link function, the log of the odds. The log counts was the link function for the Poisson or negative binomial regression. The log hazard was the link function for the Cox model. And so this may sound like tedious detail, but it should be clear from the examples that we did that you have to know what these link functions are if you want to interpret the betas. Because you'll see in many papers they just say the betas were. And that's not really helpful. I'd like them to do the transformation, say the hazard ratio was, or the IRR was, or the odds ratio was. But sometimes they don't, and you have to do it in your head, to interpret it properly, which means you have to know what the link function was. The other difference, which seems minor, has to do with minimizing the sum of error, the error sum squares, or the mean square error equivalently. As I said, the maximum likelihood procedure doesn't do that. It maximizes the likelihood, which is the same as maximizing the log likelihood, which is the same as minimizing the deviance, which is just minus 2 times the log likelihood. So you will see in the output, and we're going to see examples of this, you will see in the output that there's always a deviance reported. And you don't have to understand the definition of the deviance, but what you should understand is it's analogous to the error sum of squares or the mean square error. And in fact, for the Gaussian model, the residual deviance and the mean squared error are exactly the same number. And so what you need to remember is the smaller the error, the smaller the deviance, the smaller the mean squared error, the better the model fits. So that's it, my 5-minute overview of generalized linear model theory. Let's put this into a context. The nurses in Celia's diabetes clinic. Yeah.
Aaron can come at 9:30.
Oh, so I can just keep talking?
Yeah.
Okay. I'll talk more slowly. Thanks. That's very nice of him. Thanks. Is that okay with you guys? We just okay. So Celia, the nurses in Celia's diabetes clinic came to her a few years ago and said, "Why are we wasting all this time measuring patients' heights? Can't we just predict it, knowing their age and sex and things like that?" And they had even made a plot saying, here's the relationship between height and age in 353 patients with diabetes between 1 and 17 years of age. And they say, well, that's pretty good. Now, this is a single univariate regression model. Doesn't matter which package you use. In R, we get height versus age. In SAS, we use proc-reg, and our model is height versus age. Similarly in SPSS. The output is also similar. So this is our output. Here's how we call the model, this model, with the LM function. And our output gives us the beta hats. These are the estimates. So our intercept is 94.1. That's beta naught. And our age slope is 4.82. So it's telling us that for every year increase in age, expected height goes up 4.82 centimeters. Now, I mentioned that the procedure returns not just the beta hats, but also the standard errors. And that allows us to calculate what are called walled statistics. So the walled statistics is just a z-score. Because we know these are maximum likelihood estimates and we know they're normally distributed from the theory, we can calculate the z-score. And that z-score comes from a standard normal distribution with a mean of 0 and a standard deviation of 1. And we can look up the p-value associated with that in the table at the back of the book, or our software can calculate it for you. But this is called the walled test. And every beta in every model gets a walled test. It's not very complicated where it comes from. It's based on the normality of the estimates. You should also appreciate that the size, or that the p-value depends on how big this z or t-score is. Therefore, it depends on the effect size, which is the beta, and it depends on how precisely that beta is estimated. So anything that screws up the denominator here can affect your conclusions. And one very common cause of screwing up is called variance inflation. If you have predictors that are highly correlated, like you've included, say, both height and age, or height and weight as predictors. Well, they're highly correlated. That's called collinearity. And it's very hard for the procedure to figure out which one is actually driving the effect. And the way that gets reflected is the standard error gets inflated. And that's called variance inflation. And imagine what happens with variance inflation. Z goes down, P goes up, and you may have a statistically significant result that you've just lost the statistical significance of. So an essential diagnostic, in fact, so you may get a false negative result. So every time you do a regression, the first diagnostic I do is there's a test called variance inflation factors, and it tells you how much variance inflation is going on, and you can identify whether or not collinearity may be a problem in your data set. So again, I'm just trying to emphasize the importance of diagnostics. Here, you can see you don't have to do these calculations. The z-score or t-score is calculated automatically, just the ratio of estimate over standard error, and the p-value is calculated automatically. So here it's telling us that, that this 5 centimeter per year increase in height is highly statistically significant. Now, the other half of the output is less familiar probably. It's called the ANOVA table. It's actually fairly simple to understand. It's all based on sums of squares and degrees of freedom. So the total sum of squares just measures the variation around the mean. So I have to calculate one parameter, that's the sample mean, and so I lose a degree of freedom. So instead of 353 degrees of freedom, I now have 352. The error sum of squares measures the variation, the residual variation around the best fit line. Okay, so that's called the error sum of squares, and to get the best fit line I have to estimate two parameters, beta naught and beta 1, so I've lost 2 degrees of freedom, 351 degrees of freedom remaining. The difference between those two numbers, SSR, is the variation that's explained by the model. Okay, and it has 1 degree of freedom, which is just the difference between the corresponding degrees of freedom for each of the components. And with these three sums of squares, I can generate some helpful statistics. So one helpful statistic is called the R squared, or the coefficient of multiple variation. And it's just it's a number between 0 and 1. It's the proportion represented by explained variation over total variation. Okay, so if it's a 1, all of the variation is explained by the model. If it's less than 1, not all of it is explained. I can also do a test of significance where I compare the amount of variation explained by the model to the amount of variation not explained by the model. That's the error sum of squares. I can adjust for the degrees of freedom, and theory tells us that follows an F distribution. In this case, with 1 numerator and 351 denominator degrees of freedom, I can look it up in a book and say what's the p-value associated with that. But in fact, the software does it for me. This is the mean squared error with its degrees of freedom, so that's the average error sum of squares. This is my R squared telling me that 80% of the variability in height is explained by age, which sounds like a lot. And my F statistic, which will be around 1 if there's no explanatory power, is actually 1370, is huge, and the p-value on 351 degrees of freedom is quite small. So it's important to understand, what is this F statistic telling us? It is, does anybody know actually? So this F statistic is telling us how well the model compares to what's called the null model that has only an intercept. So in this case, so we could have 10 predictors, it would be comparing the 10 predictor model with the intercept only model. And so in this case, adding just age, we get a highly significant effect. This model has a statistically significant explanatory power. But again, I come back to one of those points that sees me jumping up on the table and ranting from time to time. Statistical significance isn't the same as clinical significance. And you'll remember we had a goal here. Our goal was, could we stop measuring heights in the clinic? And even though I have a fantastic R squared and my p-value is highly significant, my mean error is 6.5 centimeters plus or minus 5. So you as clinicians have to decide, if the nurse comes to you and says, well, a patient could be 154 centimeters or 166 centimeters with 67% probability, are you happy with that? And I hope no one's going to say yes. So in the end, you have to go back to your clinical question and say, is this result useful? Okay, so we've learned there's a relationship, we've learned it's a strong relationship, it probably isn't clinically useful. So then we ask ourselves, can we do a better job by adding more predictors? And our data set includes additional predictors. We have height and age that we've looked at, we have weight, we have sex, we have, these are patients with diabetes, we have their treatment modality, whether they're on standard insulin therapy, multiple daily injections, such as 4 or 5 injections a day, or pump therapy. We also have their census-based socioeconomic status or material deprivation quintile. And the question becomes, well, can I improve the fit? So this is a more realistic case study. Let's pay attention to some of the issues. So one of the issues that comes up is, how do we code categorical variables? And as we've seen in the labs and lectures up till now, that we often take categorical variables with 2 categories, with 2 levels, and we use what are called dummy variables or indicator variables. So that's a variable that can take on a value of 0 for the reference category or 1 for the other category. So in this case, sex 0 could be male, sex 1 could be female. And we put that into our main effects regression model. And by main effects, it just means there are only linear terms here. There's no interaction terms, there's no nonlinear terms. In our main effect model, we've just included age, which is our primary exposure, and we're adding sex. And the reason that I show you a small number formula is because sometimes it can get confusing to say, well, what is that beta telling me? Well, you can always go back to your model and figure it out. So in this case, this is our model. When we're dealing with males, the sex term goes to 0, and we have this regression equation with intercept beta naught and slope beta 1. When sex equals 1 in the females, beta 2 is now a constant, which basically means it's being added to the intercept. So we get another regression equation. It has the same slope, but the intercept is shifted. So if it wasn't clear to you what the beta associated with the categorical variable meant, you can always figure it out by going back to first principles. And in general, this is what it means. Beta naught is the intercept for the reference level, in this case male. Beta 1 is the common slope, and beta 2 is the shift in intercept. So think a more complicated setting. It's really easy when you have only 2 categories, because it only takes 1 dummy variable to code it. In general, if you have k levels, so if you work with StatsCan data, there are 32 race variables, so the k equals 32, or 32 different ethnicities that are captured in the census. So you're going to need 31 dummy variables to code for those 32 race categories. So when you think, oh, I'm just adding 1 variable, no, you're not. You're adding 31 variables, which is a lot. And so in general, as I said, sorry, I got lost here. K levels means k minus 1 dummy variables. The other day, someone was chiding me because I don't like Excel. One of the reasons why I don't like Excel is if you use its regression model, you have to create all those dummy variables yourself. In any other software, it takes care of creating the dummy variables and sets the reference level. So in SAS, you say modality is a class variable. In R, you say it's a factor variable. And it will create, in this case, there are 3 levels to modality. It will create 2 dummy variables, x1 and x2. When they're both equal to 0, that's our reference category, in this case standard therapy. When x1 is equal to 1, that's MDI, and when x2 is equal to 1, that's MDI. And if you go through the algebra again, you'll come to the same conclusion. Beta 1 associated with x1 measures the shift in the intercept when you go from standard therapy, your reference level, to MDI. Beta 2 measures the shift in the intercept when you go from your reference level standard therapy to pump therapy. So you should now be able to make sense of how categorical variables get included in a regression model. We should now talk briefly about how you construct your regression model. Particularly in the age of big data, you may have thousands of variables. Some of you may have studied statistics a few years ago and learned about automated variable selection procedures called stepwise or forward or backward, where basically what happens is the statistical software applies rigid statistical criteria based on the F statistic or the p-values to choose which variables go into the model. Statisticians used to love these. They said, oh, they're objective, reproducible, they get rid of the subjective element. They're very popular. They are no longer so popular, and I would urge you to forget everything you ever learned about them. And just to give you a reinforcing anecdote, shortly after arriving here, a reviewer wrote back and said, I don't like what you've done, please use an automated variable selection procedure. So as a joke, I said this at our staff meeting, and my boss, the chief statistician, kind of rubs her chin and says, well, you could do that, and then you're fired. So automated variable selection is no longer as popular as it used to be, largely because it's often wrong. Even when we know what the relationship should be, it often finds an incorrect subset of the variables to include. So how do you approach building a model when you've got lots of variables? In general, for a linear regression model, you need about 10 observations for each parameter in the model. For the other types of regression models, like survival models and logistic regression models, you need about 10 cases, so 10 yeses or 10 deaths for each parameter in the model to get reproducible unbiased estimates. And so if your data set isn't unlimited, you need some approach to how do I select the most important variables. So how do you do that? Firstly, you're going to use your clinical hat. You're going to use the fact that you're a subject matter expert. And you're going to go to the literature and you're going to look at what's been studied before. And you're going to think about the biology and say, well, what's plausible? And only then are you going to start doing statistical analyses, exploratory analyses. Usually, you're just going to be looking at simple correlations or single predictor models. And we give this a fancy name. We call it bivariate screening. And this is a nice definition from Vittingoff's text on regression models and biostatistics, which is a nice, actually it's a stata text. Suzanne, if you'd like a good stata text on regression models, it's nice. Vittingoff has a chapter on bivariate screening, and he basically says we evaluate our candidates one at a time in single predictor models, and we have a priori criterion, and if it meets that criterion, we include it in the final model. And by a priori criterion, it doesn't have to be statistically significant. Often I use a threshold of 0.2. Depends on my application, depends on how much pruning I need to do. So all I want is enough evidence that there might be a relationship there that I should include it. So that's kind of a judgment call. So then, let's say I've included my obligate predictors. Age and sex and pediatrics are almost always obligate predictors. So now I want to start exploring the data. Well, the first thing I do is I look at the frequency histogram of my response, my Y, and in this case height. So what am I looking for here? I'm looking at the range. I'm looking for holes in the data, and holes can be subtle. For instance, here, just to show you, I dropped all the 6 to 14-year-olds in the data set, and I made a little hole in the middle. And if I'm not paying attention, and I don't realize that there's a hole in the middle of the data, some of my conclusions may be extrapolated outside the range of the data, and therefore may be of questionable value. So it's really important that I assess the applicability of my data. I'm also trying to identify outliers or extreme values. I'm going to do exactly the same thing for each of my predictors for exactly the same reasons. I'm then going to do the bivariate screening. I'm going to look at how my response is related to the individual predictor. So I can use scatter plots for numeric predictors, I can use box plots for categorical variables, and I'm trying to identify candidates here. I'm also trying to assess their linearity. So as I've told you before, I like to put both the best fit linear regression and the best lowest smooth on, and you can see this relationship looks linear, this one looks like it might benefit perhaps from a quadratic transformation if I'm feeling that press. So my exploratory analysis is giving me a lot of input for the creation of my final model. This may sound like a lot of work, but in fact, there's a scatter plot matrix function where you just tell it the data set and it creates a scatter plot matrix, which is kind of a nice output. The diagonal shows me all the individual frequency histograms, and the off-diagonal elements show me the bivariate relationship. So this is height versus weight, height versus age, height versus sex. And so basically, I do a scatter plot matrix. And from this, I tentatively identify my candidates. And in this case, I've identified 3 candidates. I want to include age and weight and sex. And that's my main effects model. And my main effects model assumes that the slope is the same for all subjects. But I haven't yet considered interactions. And an interaction just means that the slope may not be the same for all subjects. For instance, the slope may vary by sex. And there are obviously there are 6 different interactions that I consider here. So again, you have to use clinical judgment. I'm almost always concerned about sex-specific relationships, so that's sort of an obligate one for me. And then the others, depending on the specific case. There are different ways to explore interactions. You can do interaction plots, or you can just do a regression where you add an interaction term, as we'll see in a moment, and see whether or not it's significant. So what's an interaction plot? We're just looking at the slope in the 2 sexes separately. So here you can see I've plotted males and females separately, and I've done a linear regression on each of them separately and used the AB line function to plot the lines. And what am I seeing here? Anyone want to interpret this interaction plot? Don't look at the right-hand side. So, what are these 2 lines telling me? Is the relationship the same in boys and girls? No. And why isn't it the same?
Different lines.
That's right. So if the lines were parallel, we would say there's no interaction. If the lines aren't parallel, and in this case they cross, we say there's an interaction. It's as simple as that. And if we wanted to deal with the interaction in our model, it's very easy. We take our main effects and we create a new variable by multiplying them together. So here we have sex and age with its own beta. So again, if you go back to your model, you can figure out what that interaction term means. So when sex is male, both beta 2 and beta 3 terms go to 0, and we have a simple regression line. When sex is female, beta 2 adds a constant to the intercept, and beta 3 adds an age